Hello. Testing 1, 2, 3. Sorry, I have to switch to different uh, broadcasting software. So is that better? The quality of video, is that better, or still lagging? Anyway, so I get to start. Forget about the face cam. Sorry about the quality, but I just don't use this broadcasting software very often. Right. So I just try that the best I can do right now. I just put my face cam here. I guess. Yeah, I see the lag. I guess that is the internet problem. So it's not just the software. There's all kind of different things happen today. Right, don't worry about it. At least you still can see what I write and you can hear fine, I think. Right. I lower the video quality a little bit, maybe it helps. How about it? Right. Let's start and then see what happened. Right. So last time, if you on the offline video, we talk about complex number, and then we can represent complex number and complex number z equal a plus bi as a point in coordinate in rectangular coordinate system. And then we put x on the x-axis is the real axis. And y-axis is the imaginary axis. And that's called the rectangular form of complex number. So let me draw that. So for example, we have the number z, the complex number z, a plus bi. So the a is on the real axis and b is on the imaginary axis. So this is the real axis, this is imaginary. So the point here is z equal to a plus bi. So we can represent a complex number that way. And the distance from that point to the origin, this one next one is the absolute values. There's many names. That distance is called the absolute values. Magnitude or the modulus. Of the complex number. And we write that is equal to z times the complex conjugate of z, the square root of a squared plus b squared. Right. That is in the form of complex number. Right. The example is plot and find the magnitude. Let's just write on the point first. 1 plus 3i negative 2 plus 2i and 3 minus 2i. Right. Have the coordinate system on the rectangular at x and y axis. However, we're not going to have x and y. What we have is the real and imaginary. Real is the x-axis and imaginary is the y-axis. So where we have 1 plus 3i, 1 on the real axis and 3 on the imaginary. So this is z equal to 1 plus 3i. And so the point is on the complex plane. Next, we find the magnitude. The magnitude is pretty much the distance from z to that. So this is the magnitude, or the absolute values of z. To just square root of 1 square plus 3 square, square root of 10. So that is the point, and that is corresponding absolute values. Next, negative 2 on the real axis and 2 on the real axis. So this is negative 2 plus 2i. And then we connect to the origin to have the absolute values. So if the point here is the absolute values, be square root of a square plus b square, which is square root of 8. And next we have 3 and negative 2i. So the real part is on the x-axis, the imaginary part on the y-axis. And absolute values a square plus b square, 9 and 4 square root of 13. Right. So complex number, we can put the real part as on the x-axis, imaginary part on the y-axis. Right. Now go to box C. The complex number ZA plus BI can be written in polar form. R cosine theta plus I R sine theta. So pretty much A is equal to R cosine and then B is equal to R sine. We can factor out R. We have cosine theta plus I sine theta. And in which case we call R is the modulus or the absolute value of Z, and theta is the argument of Z. So absolute values of Z or R is called the absolute value of Z, and theta called the argument of Z. So we have the modulo, absolute values of course also called the modulus of Z. So let me just draw this real quick. So instead of have A and B, sorry, this is B and A, we can have R and theta, and B A is A cosine theta, R cosine theta is R sine theta. No, this is not the problem with my computer, or it's just the problem with the network. It's just terrible right now. Right. So again, instead of A and B, we use R cosine for the real part and R sine for the imaginary part. Right. D. Example. Write z equals square root of 3 plus I in polar form. Now it's very important that this kind of problem very similar to the polar coordinates we did earlier. So if we try to sketch, we'll get the idea first and then we can always do convert to. So have square root of 3 on the real part or the imaginary on the real part, the x-axis, then 1 on the imaginary part, the y-axis, and this point square root of 3 plus 1 times I. So now we try to draw this in polar form. So if we can just form a triangle here, and we have theta, and we have R, and obviously R, Pythagorean theorem, R equal to square root of, instead of x squared plus y squared, we can write a squared plus b squared either way. So let's say a squared plus b squared square 3 squared plus 1, which is 1 square, or square root of 4, which is 1. And I cannot use a calculator, but I just have to use the old-fashioned calculator. So I will set the calculator in the degree mode first. So we have R. How do we find theta? Alright. So in polar coordinate, in the previous section, we have x squared plus y squared equal to R squared. And then of course we can get R equal to square root of a squared plus b squared. And then tangent of theta is equal to y for x. So in section 9.1 and 9.2, we have polar coordinate. We're using that. Then the same thing here. X is a and y is b. Is equal to, instead of y over x, is going to be b over a. So what we do is we let x is the same as a and y is the same as b. Instead of that, we use A and B. Right. B is imaginary part, and square root of 3 is the real part. So tangent is equal to 1 over square root of 3 to get to the angle. And okay, so the calculation is in degree mode. Tangent inverse 1 over square root of 3 so we do that. That is 30 degrees. 30 degrees or pi over 6. So we have square root of 4 is 2, sorry. So we have r is 2 and theta is pi over 6. And then we put the complex number. Instead of a plus bi, it's going to be r cosine theta plus I sine theta. So put in the information, we have 2 cosine pi over 6 plus I sine of pi over 6. Right. Next, we write the number a, the number in polar form. In rectangular form. Oh, for this, it will be a lot easier. We just multiply and distribute the 2. And then we multiply the 2 into that. I'm going to put the 2 right after the I. So I times 2 sine of pi over 3. Cosine of pi over 3. Sine over pi over 3 is 1/2. Sine of pi over 3 is square root of 3 over 2. And that cancels out. That cancels out. We have 1 plus square root of 3i, or I square root of 3. Either way. So from polar to rectangular is easy. We just multiply them out. From rectangular to polar, we're just going to find the r and theta, and then we just write the right form. Next, we use product. And quotient of complex number. Now, in section 9.3, we learn how to multiply the numbers, or add or divide the numbers in complex number in rectangular form. That's easy, but even easier when we have the numbers in the polar form. So let's look at the theory here. So let's say we have two complex number, one with R1 and angle, one with R1 and theta 1, one with R2 and theta 2. Notice that those two angles have to be the same. Now, if that is the case, then when we multiply them, it's very easy. We just multiply the modulus or the modulo, and we add the angle. Modulo and add the arguments. When we divide the modulo and we just subtract the arguments. So because we lose some time with I'm sorry, that was my phone for the technical thing. So we just go ahead and go to the example rather than go to the proof. Let's see, we have the point, the complex number z1, 3 cosine 45 degrees plus I sine 45 degrees. And z2, 4 cosine 15 degrees and I sine 15 degrees. So always like that, we have a number, positive numbers, and then the angles will be the same angles. The cosine by itself and then I sine. Right. So when we multiply two numbers together, first we multiply the modulo, so 3 times 4. And then if this is multiplied, we will add the angles. So cosine of 45 degrees plus 15 degrees. And then I sine of 45 degrees as always, those two must be the same. So we have 12 cosine of 60 degrees So it's very simple. Multiply the modulo and add their arguments. So that's what we do when we multiply complex number. What happens when we subtract? When we divide complex number, then we just divide the modulo 3 divided by 4, and then we subtract the argument. 45 minus 15 I sine of 45 minus 15 is cosine 30 degrees. I sine of 30 degrees. So that's very simple, right? We multiply the modulo and add the arguments. Divide the modulo and subtract the argument. We can also multiply it out if we just want this in rectangular form. So we have 12 cosine of 60 and then I sine of 60 degrees. If we want to, we can decide to use that as multiply it out. 12 cosine of 60 degrees. Sorry, barely can see that. So 12 cosine of 60 degrees, and then plus I, we have the 12 sine of 60 degrees, and I cosine of 60 degrees is 1/2 plus I 12 sine 60 degrees, we have 3/2. So we can write this as 6 plus I 6 square root of 3. So we can write that in rectangular form if we choose to. So what we learned so far. First, a complex number can be written in rectangular form or in polar form. So either that form or in that form. If it is in polar form, multiply and divide will be easily defined like this. Try another example. Let's see 20 cosine pi over 3 and I sine of pi over 3. And Z2 5 cosine pi over 6 plus I sine of pi over 6. And then we multiply them. Z1 times Z2 is multiply the modulo 20 times 5 and then add the angle pi over 3 plus pi over 6. So that is 100 cosine pi over 3 plus pi over 6. One over 3 plus 1 over 6. That is 1/2. And we stick a pi to it, so pi over 2. And those angles must be the same. So that's what we have. And then when we divide the modulo 20 divided by 5. And then we subtract the arguments. That gives us 4 and 1 over 3 minus 1 over 6. 1 over 3 minus 1 over 6 is 1 over 6. It is 1 over 6. And we stick a pi to it. Right. So that is multiply and divide. Actually, let's take a few minute break, and then we'll continue. We continue 225. There's no way I can improve the internet, but at least I might change the setting a little bit so it look more like usual. Right, we continue. Right, at least it look kind of like normal. Right. So next part, we have the Morris Theorem. First, if we have z is r cosine theta plus I sine theta, to the number, complex number in the polar form. That is a complex number by the way. Look like the internet is stable now, and there's no more lag, and quality should be back. So I really don't know what happened. Yeah, it showed that the speed are much better now. So what do we do in the Morris theorem? So what we see is that when we have the power of a complex number, the modulo raised to the power, and then the multiply that number into the argument. So there are two parts. Oh, thank you. I have no idea. So modulo raised to the power of n. So it's not about the broadcast software, it's just the internet, and I don't know why we switched to this, but that's okay though. So the modulus or modulo raised to the n power, that modulus singular, modulus raised to the power of n, and then the argument multiplied by n. So that is where we raise a number to that. Let's look at the first example. Let z equal 1 plus I, and then find z to the fourth. Okay, let's see if we can do this on the calculator first. Right, we did this back in complex number, section 9.3. Right, so if we want complex number, hit mode and make sure that hold it very closely, and make sure that it is in the complex number, meaning that we select a plus bi. Right, That's good, right? And then second, hit second mode back to the home screen, second mode. Right. Now we just type 1 plus the I. The I is the decimal point. Just hit second and decimal point, second and decimal point. So 1 plus I raised to the 4th power. We have -4. Right, so we have -4. But can we do that? So first of all, we know that 1 plus I to the 4th power. We just multiply that 4 times and give us -4. So that's easy. Now how do we apply the Morris Theorem? So first, we have Z equal 1 plus I. We have to convert this to the polar form. So it's always helpful if we draw the point out. This one is 1 on the x-axis and 1i on the imaginary axis, and 1 plus I is this. Right. And so in that case, we will find two things in the polar form, which means there will be R and there will be theta. So R is that and theta is this angle. So R is square root of a squared plus b squared. Instead of x squared plus y squared, it is r squared a squared plus b squared. So square root of 1 square. B is also 1. So we have square root of 2. And then next we have tangent of theta is y over x or b over a 1 over 1, which is 1. Now tangent is equal to 1 to get back to the angle. Tangent inverse of 1. We can use this in degree mode if we want to. Sometimes it's easier to just use the degree mode. So tangent inverse of 1, that's 45 degrees. So it is easier to use the degree mode actually. So that's 45 degrees. So that instead of 1 plus I, we can use R is equal to square root of 2 and theta 45 degrees. And then we can write the numbers in complex, in polar form. R cosine theta R cosine theta plus I sine theta. So in this case we have the R is square root of 2 and then cosine of 45 degrees, I sine of 45 degrees. So that's the first thing we do, convert a rectangular form to polar form in that way. And then the Morris Theorem is Very simple. We raise everything to the fourth power, right? Now we have the fourth power. And with the fourth power, we raise the modulus to the fourth power. And then multiply the argument by the same number. Right, 4 times 45 is 180 degrees, and square root of 2 to the fourth power. And then square root of 2. If we rewrite square root is equivalent to power 1/2. In general, if we have a number m over n is the same as m and n. So in that case, we have square root of 2, which is power 1, square root is 2. The power on top, index is radical at the bottom. So we use that formula, and that's what we have. Then we have 4 times 45 degrees, that's 180 degrees. And 2 to the 1/2 times 4, when we multiply the powers, a power to another power, we multiply them. So in that case, we have 2 to the 1/2 times 4, so that is 2. 2 to 1/2 times 4 is 2. Cosine of 180 degrees, that is -1. And sine of 180 degrees is 0. So we have 4 times -1, which is -4. So of course we use a calculator. We have -4, and now we have -4. So the modulus is raised to the power, and then that power we multiply to the argument. Let's look at another example. Let z equals square root of 3 plus 2, find z cubed. 2i, sorry. Right, first, we'll convert z equal to square root of 3 never mind, can you change this to 2 square root of 3? Yeah, the number will look better that way. Right. So first we'll convert this number to polar. Right. Of course we can draw the same thing, but here we just use R is equal to square of A square plus B square. So 2 square is 4, square root of 3 square is 3, and then plus 4. So this is 4, 12, 4, 16, square of 16 is 4. So we find the modulus of the complex number that way. Next, tangent is equal to y over x or b over a. So b over a. Cancel the 2. We have that. So then when we find theta, is tangent inverse of 1 over square root of 3. If you put this in the calculator, it will be 30 degrees. Right, and just to make sure that we should draw sketch a number and see if it is in the right quadrant. 2 on the x-axis and 2 square root of 3 on the x-axis and 2 on the y-axis. So it looks like it is 30 degrees in the first quadrant. By the way, if we do the tangent inverse and it does not come to the right quadrant, we need to add 180 degrees to it to go to the right quadrant. If the point is in here, we have to add 180 degrees to it to get to the right quadrant. Right, bottom line is R is that and theta is that. So now we get back to Z. We write that as polar form R times cosine theta plus I sine theta. So in this case, Z equal to 4 cosine 30 degrees plus I sine of 30 degrees. And then we want to cube. If we raise that to the power of 3, raise the power to the modulo, and then the angle multiplied by that number. Right, 4 cubed is 64 cosine of 90 degrees plus I sine of 90 degrees. Now, cosine of 90 degrees 0 and sine of 90 degrees 1. So we just have 64 times 0 plus 1 times I, or just 64i. Right, so let's see if we use the calculator. 2 square root of 3 plus 2 and then second the decimal point to I raised to the third power. And indeed we have 64i. So simple enough. If the number is in the polar form, the modulo we raise to the same power and the argument is multiplied by the number. So that's all we do for the powers. Right, last thing we learned in this class is the end root, also sort of part of the Morris theorem. So the end roots. And the key here is it is blue rose. Of complex number. The theorem here is this will be part D. The end root is a K of a complex number W equal to R cosine theta plus I sine theta, where R is positive. Z sub K equal to R to 1 over N cosine of theta plus 360 degree divided by K plus I sine theta plus 360 degree times K divided by N. I just draw that completely wrong. Times K and divided by N. And then 4K 0, 1, and 2 up to N minus 1. Right. And we can also use 2 pi instead of 360 degrees. Right. So our first thing we do is, by the way, this is the same thing as the end root of R. So we take the modulo and then take the end root. That's the first thing. And then this, the K, we take the values from 0 to N minus 1. So there will be N answer. So there will be 3 cube roots, 2 square root, 4 fourth root, and then you get the idea. Right. D. And then this will be E example. Our 5 ohm three cube root of 1 plus I. And the key is there are 3 cube roots, and we're going to find all of them. Right, so first, this is the step that we always have to do, is write this in polar form. So first, convert z equal 1 plus I to polar form. And we already did that on the previous example. Z equal 1 plus I is equivalent to square root of 2 cosine 45 degrees I sine 45 degrees. See previous example, and we have z equal to square root of 2 cosine of 45 degrees plus I sine of 45 degrees. Right. Now we apply the theorem. The theorem say the only 3 roots. By the way, cube root, because it's cube, and it's equal to 3, right? So in that case, we say z sub k equal to, right, the theorem say we're going to take the cube root of square root of 2, or we just have the modulo to the 1/3, right? Same thing. So n is 3, so this is 1/3, and we have square root of 2. Right, next. According to that theorem, we're going to get that angle 45 degrees plus to 60 degrees times k divided by n. Then that number n will be 3 plus I sine 45 degree plus 360 degree times k divided by n, which is 3. Notice that this k is the same as this k, and k will take the values for 0, 1, and 2. So for k equal to 0, 1, and then 2, there are 3 cube roots, 0, 1, 2. Right. Now for k equal to 0, we have z sub 0 equal to square root of 2 to 1/3. Earlier we have square root of 2 is 2 to 1/2. Now we have 1/2 and then to the 1/3. K equal to 0, so we just have 45 degrees divided by 3. Now just say 360 degrees times 0, because k is equal to 0, plus I sine 45 plus 360 times 0 divided by 3. Multiply, raise the power to another power. We multiply the exponent. 1/2 times 1/3 is 1/6. And then we have cosine 45 divided by 3 is 15 degrees. And 45 divided by 3, so 15 degrees. So there's one of them. And next, for k equal to 1, we do the same thing. Put 1 in for this k, and that all of those k. Z sub 1 equal to. Now we know that this is going to be 2 to the 1/6, but it will be the same. And then cosine 45 degree plus 360 degree times 1 divided by 3 I sine 45 degree plus 360 times 1 divided by 3. So already did this 2 to the 1/6. 45 plus 360 divided by 3. That's 135 degrees. And then, so that is another answer. This will be 6. And then we need one more for k equal to 2. Z2 will be equal to square root of 2 to 1/3 cosine of 45 degrees. Now k equal to 2. 360 times 2 divided by 3 I sine of 45 plus 360 times 2 divided by 3. And we already did this 2 to the 1/6. And then cosine, what is 45 degrees plus 720 divided by 3, 255. So there are 3 cube roots, and you have 3 answers. 1, 2, and 3. Corresponding to k equal to 1, k equal to 0, and k equal to 2. So just put in there, we have 3 cube roots. Right. One thing we note about this solution. Notice the angle of 15 degrees, 135 and 255. If we think about that, is 0 to 360 degrees, one complete revolution. 15 degrees, 135 and 255. The angle always divides the circle evenly, so you can see that you add 120 degrees, you add 120 degrees, and then you can add 120 degrees to get back to those. So whatever the answer is, whatever the argument for the problem, it's always divide 360 degree evenly spaced. Right. So we do one more of this to make sure that we have it. So one more sample. 2. Five own square root of negative 4i. So square root means that n equal to 2. And because of that, we're going to have 2 square roots because n equal to 2. Right. But always first convert that number to polar. So let's try to draw it out. Negative 4i it is here, right? Because I imaginary is on the y-axis and negative, so it is over here. So if we go the angle, that would be 270 degrees, and the modulo, the absolute value is 4. So negative 4i is equal to cosine theta plus I sine theta. The modulo absolute value is 4. The angle 370 degrees. Right. So we have 4 cosine 270 degree plus I sine 270 degrees. Right, so we write the numbers in complex in the polar form. That's the first step. Next, we use the theorem. The theorem say the root, the k root, so we're going to raise that number to the reciprocal, n equal to 2. So this is 1 over 2. And then cosine. I'm going to add 360 degrees times k divided by n. And then plus I sine 270 degrees plus 360 times k divided by 2. So 4 to the 1/2, that is 1/2 power is the same as the square root of 4. Just write this again. 270 plus 360 times k divided by 2 plus I sine 270 plus 360 degree times k divided by 2. So we write the formula general like that first, and then we choose for k equal to 0 and then k equal to 1. Since this is the square root, we're going to need 2 of them. So k is go from 0 and then 1. If we have cube root, there are 3 of them. We go 0, 1, and 2. So by all here we mean there are 2 square root of negative 4i. Right, we'll just write out z sub 0 because k is 0, square root of 4, which is 2. That's just silly. Right, 270 degree plus 360 times 0 divided by 2 plus I sine 270 degrees plus 360 times 0 divided by 2. 270 divided by 2, that is 0 by the way. So 270 divided by 2 is 135 degrees. And then next, we put 1 in for k. 270 plus 360 divided by 2 is 315 degrees. So there are two square root of negative 4i. This is the first one, and this is the second one. Of course, we can convert this back to rectangular form, but I think we're just going to leave that in polar form. On the test, on the final, it's fine just to leave it in the polar form like this. Again, cube root, there are 3 of them, so k equal to 0, 1, and 2. Square root, there will be 2 of them, because square root, square mean 2. And one more thing, 315 and 315, 315 degrees and 135. So 135 is right there, 135 degrees, and then 315 is on the other side. As mentioned before, whatever the arguments of the problem is, it's always evenly spaced out of the whole circle. Later on we call that root of unity. So if there are 3 of them, those 3 will divide the circle perfectly in 3 segments. Here we have 2, so divide the circle into half, 1 and 2. Or we just go 180 degrees to the other one and back another 180 degrees. So the answer always like that. The arguments always evenly divide a circle. Alright. And with that, that is the end of the note. And this is also the end of the whole trigonometry. Once again, I'm sorry about the technology, the technical difficulty today. And that pretty much summarized the whole semester, right? We always make things on the fly, do things on the fly. Right, so we will have the review on Thursday, unless if you can take the sample test on the responders. If you took the sample test, I will send an email saying that you successfully took the test, so you can take the test at your own time using responders lockdown browser. If you cannot take the sample test, or you just want to take it during class time, then I will see you at 1 o'clock. You're welcome. They will see you on 1 o'clock on Thursday. Alright. I will send you an email to tonight. We'll summarize what do you need for the final, and how what do you need for the final in terms of, like, do you need the Morris Theorem, you need how to do double angle, something like that. I will give you the checklist of what you need to know for the final. So that's the list, the first one. Second is how do you take the test. If you are taking responders, that's fine. If you're taking the test with me on Thursday, there's a few things that we have to check as well. And make sure that you turn in everything. If up to this point you have the core assessment, I think it's due on Wednesday, tomorrow, and you should turn in on the note, the written note. I send you the list of what you need to send back. And if you send back already, I already put the grade on the grade book, so just go to eCampus and see the grade book for that, for your grade for that assignment. Right, do you have any question for the remaining of the class? Right, so watch out for that email tonight when I send out about the information about the final exam. Oh, yes, I'm glad you bring that up. So, because this is a test and online, and so it will be very difficult to enforce the rule that you do not allow to use note or not. So the final exam is 30% of the course. Yeah, final exam is 30%. So the quick rundown. You have the note or the participation. So participation is 10%. The homework 15%. 3 tests 45% total, and that's 70 total up to this point, and the final 30%. The core artifact assignment is the plus 3% for the core assessment. Right, so that's the breakdown of the course. So if you took the test and the homework or participation, you have 70% of the class already. Now just need to take the final. Right, the final though, even though all of them are multiple choice, but there will be 5 questions. There will be 5 questions that you need to take the picture and send back the work within 1 hour. I will send an email tonight and explain how to do that. So pretty much where you send back the note for the participation is the same place you submit the work for the final exam. So after you finish the final exam, take the picture of those 5 questions, send it back to the same place, and that will be for the final. On the multiple choice will be 90%. And then the 10% is for the written work that you send back. And the written work you send back within 1 hour. Even though if you take the test with responders, it shows you what time you take the test and when you finish the test. And then I will count 1 hour from that time until where you submit the work. So it have to be within 1 hour to be counted. Right. Any other question? Right. Like I said, I will send you an email tonight about the final exam. Yes, if you take the test on Wednesday, finish at 3 o'clock, 3 p.m., then I expect the work be sent by 4 p.m. Yes, because it does show what time you finish the test, and I will count from 1 hour when you finish the test until you send the work. It have to be within 1 hour. And only 5 questions show about 5 pictures. So it's not that big of a deal. Make sure you send in the same place where you send in the note. And also, if you take the test on Thursday during class time, before the test, go to your email. I will send you the link, either Zoom or some kind of conference, video conference. Yes, so I will send you the Zoom link. You click on that link so you can turn the video conference. You have to have the video in order to take the final. Yeah. So if you take the test with responders, you do not need the password. But if you take the test with me, you need the password. And when I see your picture, I'll give you a password. Yeah, you have to have the video in order to have the password. Okay. And the most important rule when checking the final is I let you use the note, I let you use the calculator, but you cannot use the cell phone, your cell phone or computer to look up the answer. So no external help, including the internet. You cannot talk to another people or another person during the test. So it's just you, your note, and the calculator. I think that's more than enough. Right. The homework and test review. If you make 90% or more, I will grow to 100. I think look for the important course information. I pretty much put everything there. The homework. Yeah, so the grade, you probably won't see it in my math lab, but I have to download the grade book on my computer and then do the rounding, a lot of calculation offline later. And just like when we talk about the 3 tests, the lowest one is 9%, and the others have 18% each. Sorry, kind of small, but I think, yeah. So that's what it is. So when you take the 3 tests, whatever is lowest, I will count that 9%. The other better test, that will be 18%. Right. Oh no. When you take the test, it just shows that you don't use your keyboard and you don't talk to anybody. So that's pretty much. If I see you typing on, because this is multiple choice, right? So there's no business of using the keyboard. You just click on the answer. There's the circle A, B, C, D. Just click on it. So you only need to use the mouse, your calculator, and the note, and have to add your mouse, the computer mouse there. But don't use the keyboard. Don't talk to anybody. That's pretty much the rule. Like I said, I will send out an email tonight. If you take the final in class, that will be next Thursday from 1 to 3. If you can take the test with responders lockdown browser, you can take it at your own time. So that's why I post the sample test. If you can take the sample test, you can take it at your own time using responders lockdown browser. Yeah. Right. Do you have any other question? This Thursday, of course. The finals this Thursday. I have to turn in the grade on Monday. So the course will finish by Saturday. On the homework, on the test, and everything will be done by this Saturday. If you take the test at your own time, it has to be before Saturday as well. So this Saturday. But our test, if you're not using responders, it has to be Thursday. Actually, I got your note and I posted your grade for that already. Just go to eCampus and check your grade. If you submit the note already, you should be able to see your grade there. And once again, I apologize for the technical difficulty at probably 15 minutes or more, half an hour before it get better. At least it's stable now, and you can have all the question answered clearly, I hope. Alright, so I guess I don't have another question, but like I said, it is an unusual semester, and when I look at the grade book and the progress of the class, it is a lot better than I anticipated. Yeah. Even though I wish we could have more, I could have more people doing the live video on YouTube, but then again, I recorded the video and it's kind of an online, so it's difficult to expect you to show up on every day. Yeah. So the test probably it is there already. I just need to click one button to make it available. So probably by midnight tonight, the test will be available. And like I said, there's a lot of unexpected thing, and you all did very well. So thank you very much, and good luck on your final. Be on the lookout for an email about the final exam, the information about the final exam. That's very important. Right, good luck. Right, I'm going to end the stream here. Right, take care.